So we will we'll talk about cost function in the neural networks. I hope you remember what is the basic neuron or a building block of the neural network, right?
Yeah.
So let me again draw it. If these are my features, this is my input. Okay, let me say 3 cross 1 input. Then it will be summed over here. Right? Okay, so if I write the whole output, how does it look? It will look like this. Right? Now, what are the limitations? If I want to solve any of the problem, let's say AND problem or problem or NAND problem or NOR problem, NOT problem, etc. This neural network can fit it nicely. I mean to say, this basic neuron. The name, the terminology that is given to this basic neuron is known as perceptron. Okay, perceptron. So when we see this perceptron is nothing but making or trying to identify the hyperplane, right?
Yeah.
So if these are my one class and these are my another class, then it will try to identify this nicely. Right? This is my hypothesis.
Wait, what is the perceptron again?
Perceptron is name of this network. This
Okay,
one, the
okay.
basic neuron is known as perceptron. Okay, if an x1 and x2. Now what you observe? We observe in this particular graph, the classes are linearly separable. Right? Second point is, now if my degree of whole data, now I have two set of features, right? X1 and X2, right? Then my hyperplane will be, if n is the degree of my data, then n minus 1 will be the degree of the hyperplane. Simple, right? Because hyperplane is my having this derivative, right? If I do the derivative of xn, it will be n into xn minus 1, n minus 1 degree. If x square, then it will be 2x, 1 degree, right? So 1 degree less than the data set, right? Now, if when we have this AND or NAND, NOR, NOT, etc., the data are linearly separable. How? Let us see this AND, right? AND is nothing but x1, x2, y. Right? This is for AND. Now when I plot this AND, how this AND will look? 0 0 0 1 1 0. Okay, so first is 0 0. So it is 0. Another is 0 1. Right? 0 1 1 0 1 1. So when I say this is like one class, circle, and this is my another class. Right? So definitely I can get a hyperplane which can easily intersect. Right? Now when I go for, let's say, OR, what it will be? 0, 1, 1, 1. So how this OR will look? Now 0, 0 is 0, other are 1. So when I plot, this will be my one class, this will be my another class, right? So I can easily draw an hyperplane which can distinguish between two classes. Now NAND will be something like this, will be 1, 1, 1 and 0, right? So this will be 0, this will be 1. This is my NAND. So here, this is my whole class, one class, this is my another class. You can get to hyperplane over here. So you are looking into this diagram, right? How this hyperplane is separating the whole two different kinds of classes, right? So we can understand this perceptron draws linear hyperplane. So as long as our bowling team is doing good bowlings, then we don't have to worry about our scores, what the opponent is scoring, right? We can definitely chase it out. But when there is a situation where we cannot separate, where this model cannot fit, we'll face some real issues. So that kind of issues came when this gate came into the picture, XOR. What XOR is all about? If I have x1, x2 and y, tell me what it will be. 0, 0, 0, 1, 1, 0, 1, 1. What is XOR for all this?
I think it will be 1. Sorry. Yeah.
Right. So when I draw this one, how it will look?
We can OR gate, but with two sort of like that. Okay.
Right. Now when I try to separate the whole of the classes, this is my one class and this is my same class, right? And the other two classes will be, right? So see the differentiation of the spaces. So I can't find any linear hyperplane which can try to distinguish this. So this is a completely non-linear problem.
Wait, but for AND, I just wonder, for AND, how was it again?
Okay. So AND is what? x1 into x2. 0 into 0, 0, 0 into 1, 0, 1 into 0, 0, 1 into 1, 1. Right? So this is my AND. So when I draw it, so it will be 0 over here, others will be, this is one class, this is another class. Okay?
Okay. But how can you differentiate like which is X class, which is O class?
Okay. So here you see, these are one value, right? And this is another value. So when I want to see what my y is trying to predict, my y is trying to predict 0 or 1. Yeah. Right? So 1, I mean to say 0 can be your O class, 1 can be your cross class. That is your criteria, how you will try to differentiate between the two classes, what letter you will be giving. Okay.
Yeah.
So let me just give you one quick assignment for you, because otherwise if
but in that AND gate graph, those two X's are actually O's, no? Because they were 0, right? y was 0 in that case.
Okay. Sorry. Yeah, I just made it a bit. Okay, so this O is O, this one is O, this one is O, and this one is X. Okay, sorry. Right. Yeah. So you try to draw this AND gate, OR gate, NOT gate, NAND gate, XOR gate, then NOR gate. Okay, draw the write the table alongside the this figure distribution graph. Giving you 10 minutes. Can you write down and send me in WhatsApp? Okay. Otherwise, if you just try to stuck over here, then it will be a bit problem. So I want you to do it so that it will be in your mind. Okay, 10 minutes. So it's 49. I'll give you till 11:59.
Okay.
Hello. Done?
Yeah, done. I'm just doing a first photo of it. Right?
Yeah. Can you see my screen, right?
Yeah.
Yes, correct. So basically what I wanted you to understand, that any of the all cases except this, or when it is other cases, we can easily identify the hyperplane separating, right?
What if it's like not?
Okay, when it is not is something like this, right?
Yeah.
If x, there is x bar, right? So when I write x here, only one input. X bar is when it is 0, 1, it is 1, 0. Okay. So if it will be only kind of a, I can write it if it is 1, 0, 1, 0. So basically not is used only to invert some of the inputs. So my if it is x is coming, I'll put the not, so it will become x bar, and then I can use some other kit. Okay. Yeah. So what basically I wanted to tell you that this perceptron is nothing but a linear model. Okay. Now when XOR comes into picture, right? So in that case, it will be something over here and here, and it will be here and here. So this is one class, and these are the other class. So here nowhere we can try to identify as a linear hyperplane that will try to separate it. So what we can do, as I told you during the linear regression curve, what we'll do, we can do, or logistic regression, sorry, we can try to make this one as a class. Let's say this is my black or gray, and this is my yellow. Then I can easily find one hyperplane. It will be something like this one. So this is H1, right? Again, I will go over here. What I will do, I will try to tell that this is one class, and this is my another class. Then I can find one more hyperplane which will be able to divide these two. And this, let's say this is H2. Right? So how I deduced this whole scenario? Right? How it did? So I told you this hyperplane is made by one perceptron. And this hyperplane is made by another perceptron. Right? So when I mix these two perceptron, what it will be? Let me say this is my whole one x1 and x2, right? X1 and x2. Now there are two perceptron, right? Two perceptron are there. So this went over here, this went over here, this summation, then this is output one or hyperplane one, then this is another one. Right? Now once these two are there, I can merge this one into another one and then I can find how it will look, right? Can you understand what I mean to say?
What do you mean by merging? Merge it.
One minute. Let me find that particular graph. Okay. So this one will be giving your output one for this hyperplane. Let's say this is the hyperplane, okay? And this is giving me the another one for this hyperplane, right? Now I have to merge this one to get or deduce my whole one result, right? So what I will do, right?
Okay.
Right. So what I try to do, I try to make, so when this one is over here, this is one my result, or this is one neuron, and this is my another neuron. So you can say neuron 1, and this is neuron 2. So what I try to make, I try to find a nonlinear function using two linear functions, right? So whenever I'm trying to face any complex nonlinear separable plane, separable sets, what I will try to do, I will try to take many linear models and deduce the nonlinearity. Okay. Yeah. So what we have understood? We have understood this basic intuition of neural network and everything. So let me go into the next topic. Next topic is in linear algebra, or neural networks. I will try to find out what is feed forward. Okay.
Yeah.
So last time we we understood what the multi-layer perceptron will be, right?
Yeah.
Multi-layer perceptron is more than one hidden layer. Do you remember what is hidden layers?
Yeah.
Okay. So in that one, if you try to see, this is my one neural network of two hidden layers, and each hidden layer has 4 neurons, and this is my output. Okay. So these will be fully connected, right?
Yeah.
And so on. So if you see what this whole network is trying to do, it is trying to have my input towards the input layer, then using the hidden layer trying to fix the parameters, fix the model, and then give me my output. So if you see, the flow is like this, one direction, right? So that's why it is known as feed forward network. Why? I'm feeding it here, then moving forward, right? So here in this particular layers, hidden layers, what is happening? It's not our botheration. We have to tune it and fix it so that we arrive at a desired output. Okay, now try to remember how my linear regression or logistic regression was happening, right? I try to assign these these are the inputs. I try to assign these weights randomly and then go for gradient descent, right?
Yeah.
But there, what was the thing? If I try to write linear regression, logistic regression, I have this will be my input. Here, definitely this summation is happening. Then here the function is happening. Then output is coming, right? So once this output, a result is there. I mean to say the predicted value is there. Let me say yp. I will match it with the ya and try to find the error. Right. So let us write how that will look. Let's say we'll take the logistic regression into the picture and try to find an analogy is for the neural network. Okay. So for any of the algorithm, what are our steps? Okay. So our first step is to randomly assign the weights. We can do random, or we can use it some predefined conditions to limit our weights or to assign our weights. Once this weights is assigned, we'll try to find what is our predicted output, right? We'll find the cost function. Why I told the cost function? Because this is the main function which will be optimized to get the desired result, right? How this cost function will be optimized? Using some optimization rule. What are the optimization rules that we have understood? That is gradient descent, right? We'll tune the weights. When the weights are tuned or the error is minimum, model is ready.
What's after cost function? You circled there.
Okay, I'll tell you it. Okay, so now let's say what is our logistic regression cost function. Can you tell me? Sorry. Right? This is my cost function of logistic regression.
Yeah.
Now remember, if I use this, so I told you, right? Our cost function can have two terms. And tell me first term and second term. Right?
Yeah.
So this is my error term. If I use the regularization, how it will look? For easy calculation. And m is the mean. Right? For simplicity, let me take 2 norm. When I am taking 2 norm here, I can write this one also. So it's an easy representation. So whole my j omega became 1 by 2m or I can say summation j is equals to 1 to m, because it will be the sum of all the w. Okay, so this is my whole regularized cost function of logistic regression. Now remember, in logistic regression we have only one set of values, whether it is logistic or linear regression. We had only one set of theta j because we didn't have any hidden layer concept or anything, right? So when I'm moving to the hidden layer concept, what will be my j theta of neural networks? So it will be Okay, so why I have used these two terms? If you see the neural network, these are nothing but I have taken two hidden layers. For that reason, I have used two summation in the weights, because there will be two set of weights, right? This is one set of weights. Sorry, one more will be there. There are three set of weights. So this is my W1, this is my W2, this is my W3, right?
Yeah.
Right. Now try to understand why I'm doing this. Okay. In my logistic regression, my input was coming, right? I was having the weights, then my output was coming, then error I was trying to reduce and was to minimize it, right?
Yeah.
Updating this weight, error, calculating my J theta. Okay. So once I have done my J theta calculation, the next step is my gradient descent. Theta nu is equals to theta old plus.
Wait, but one note.
Yeah.
So in those two sigmas, what is that? H1 is equal to?
1 to L minus 1.
What is L minus 1 in this case?
Okay, so if I say what are the number of neurons, I can say L, I can take. Okay, number of neurons in this one, let me say total number is L. Let me say L1, and this one is L2. Okay, so total number is L1 and L2. So why I want to do this? Because if I have set of W1 is equals to W11, W12, W13. So lambda of W will be W11 square plus W12 square plus W13 square. So this is the set of weights that I want to use in the regularization. When only one set of, let's say, logistic regression. In case of linear regression, neural networks, I have here set of W, here is set of W, and here set of W. Right? So three kinds of W's are there. Or if I take only one hidden layer, also two will be there. Right? When there is no hidden layer, there will be only one set of will be there. Right?
Yeah.
So that's why I have to just remember. Don't remember any of the mathematical formulation. Remember sum of all the weights. As simple as it is. Okay. Don't remember these complex mathematical formulations. Try to understand what we are doing, what you are doing, why you are doing this. Because you have to limit your weights. That's it.
Alright.
Okay. So done. So I'm reducing this cost function and optimizing the theta nu. Same thing over here. Okay. Now this is my input coming. This is my hidden layer 1. This is my hidden layer 2. This I'm getting my output. So once I've got the output, I'll find the error. Now I have the first set of weights. Okay. So I will deduce theta 3. So once I have deduced the theta 3, now here I have another set of weights. So I will deduce theta 2. Now once I have deduced the theta 2, I have another set of weights, that is one I have del by theta 1.
Wait. What is the linear regression formula? Theta all.
Pardon me?
That linear regression formula. Theta nu is equal to theta all plus what? What is that before dj theta?
Which one you are trying to say? This one?
Yes.
This is gradient descent formula, no?
So yeah, gradient descent. But what is that before dj theta?
Oh, this is okay. This is learning rate, I wrote.
Oh, okay.
You can write it alpha or you can write it eta also. Any, but this would be your learning rate. I'll write it learning rate. Okay.
And this shows the gradient descent of the neural network, or?
Okay, gradient descent of neural network. I tried to. It will be slightly complex. Okay, so can you see this page PPT or on the whiteboard you are looking?
Whiteboard.
Okay. Can you see now?
Yeah.
Okay. So if you see over here, I told you this logistic regression cost function is this. Neural network cost function will be my summation of the hidden layers. So that is what it is written over here. Okay. Now what I'm trying to do over here, that the whole concept is known as back propagation algorithm. Okay.
Yeah.
So why it is back propagation, I'll tell you. So neural network is what? Neural network is feed forward network. You have to go forward, feeding the input. Once you have got the output, you will minimize the output. You have to go back. Okay.
Yeah.
Tracing back the error to minimize the error. But there are a lot of hurdles, right? So each hurdle you have to jump. So how you will jump? You will try to minimize the error at each step of the hurdle. There are 3 hurdles over here. First hurdle is your input hidden layer 1 weight. Second hurdle is your hidden layer 1, hidden layer 2 weights. Third hurdle will be your hidden layer 2 and output weights. So these all you have to optimize. Okay. So your gradient computation will be, you have to minimize your cost function. And what you have to compute? You have to compute the gradient of each of the weights. Okay. So if this is my output, then gradient of this, gradient of this, gradient of this. Just remember, that is what it is whole written over here in this whole scenario. Okay. Simple rule. Whole scenario, it is tried to written mathematically everything, but simple is, I have the output, I'll find the error. My error will be in the form of cost function. I have to minimize the cost function, updating the weights. How I'll be updating the weights? At each of the level. So you can say, I'm trying to find the gradient descent over here for the weight of this. I'm trying to find the gradient descent over here for the weight of this. I'm trying to find the gradient descent over here for the weight of this. Right? So if I tell you how does it will look, so you might have seen the calculus, right? D of dx1 L will be dl by dx2 into dx2 by dx3 into dx3 by dx1, right? Multiplication. This is multiplication, or what is this? Gradients for different variables.
But what does it show? What is dl by dx1?
Okay, so let's say d of dl is in the function of x, y, and x. I want to find d of t, where y is equals to f of let's say f of t, and x is equals to, let's say, f of y or something. So I want to try to say d of l by d of y into d of x and d of x by d of y into d of y by d of t. So if I L is in the function of y and x, right, and x in the function of y, and y is in the function of t. For example, let's say L is equals to something. How can I try to? How much you have learned in calculus? What all things?
I've learned a lot: differentiation, integration, and
Okay.
pretty much everything.
Okay. So if my f of xy is equals to x square plus y square plus 2xy. Okay. I want to find df by dt. Okay, in this x is equals to 2t, y is equals to x square. Can you find it out how it will be?
Yeah. So
Right, you have to put all the values and you will get it, right? Have you learned about this multiplication rule?
yeah.
That is what I wanted to try to say over here. So now my L, if I write it, or my J of theta, right? So what I, okay, so my output, how my output will be looking? F of W3T into W2T into W1T plus bias 1 plus bias 2 plus bias 3, right?
Yeah.
This is what my output. So when I'll be getting my this y predicted will be in this form, right? So how my j theta will look? J theta will also have these all values, right? Because in my j theta, the first term error is nothing by h of theta, is a function of h of theta, and h of theta is nothing but I'm trying to find this whole of h of theta, right? So it will be in this form. Plus I have to find or I have to regularize all my weights W3, W2, W1. Right? So these all are there. So this my whole cost function is nothing but j of theta 1, theta 2, theta 3. Right? Yeah. So when I have this, now I want to minimize. Let me say this is my hidden layer 1, this is my hidden layer 2, this is my output, and this is my input. H1, H2. Okay. So once I found this here, in this particular step, I have W3. I will optimize J theta 1, theta 2, theta 3 with J theta 3, right?
Yeah.
I have optimized J theta 3, I will optimize my W3. Once I have done, still my J theta will have now theta 1 and theta 2.
Yeah.
Right? So I will over here, I have my theta 2, so I will find J of, and I will optimize my W2. Done. Now here, now it will be having my theta 1. So I will be optimizing. So this everything is happening in one step. Okay. So that is what he is saying over here. So first step delta, second step delta, third step delta. Okay. So just try to understand, just remember what is happening. So you are looking at this PPT, right? You can see the PPT, right?
Now only whiteboard.
Okay, whiteboard. Wait. Okay, so here theta delta 1, delta 2, and delta 3. Okay.
Yeah.
So that is, just remember what is happening. You don't have to buy hard the formulas and everything. You can buy hard the formulas looking into the books or PPTs. But that is the basic intuition behind this backpropagation algorithm. Okay. So now if I ask you, what is the algorithm by which the weights are optimized in linear neural networks, what you will say?
Using the cost function gradient backpropagation algorithm.
Exactly. So what does backpropagation does?
It identifies the error, right, and minimizes it. Or?
Exactly. At each step, or each step here, each step will be all the hidden layers, or where all the weights are there. Okay.
Yeah.
So this I try to give an intuition. The same intuition, these form things will be there. Okay. This one you can see. If any issues, then you can ask me.
All right.
Don't need to go to any deep things. Everything is, in books or everywhere they will try to give you maximum more information, but your whole intuition is that. Okay, so here you can try to understand those things over here. So we have understood this nonlinear hypothesis and advice on these all things will be understanding. So I'll do one thing. I'll stop for 15-20 minutes right now.